Imagine staring through the void of space, far beyond the comforting blue swirl of Earth, past the crimson deserts of Mars and the swirling storms of Jupiter, to a tiny, icy world gleaming like a pearl against the blackness. That world is Europa. And now, for the first time, we are seeing it closer than we ever have before. It isn't just a moon. It's a mystery box wrapped in a frozen shell, hiding secrets that may rewrite everything we know about life in the universe. Something is happening beneath its surface. Something ancient. Something alive, perhaps. And with every new image and data stream, we are peeling back the layers, ice, time, and uncertainty, getting ever closer to the truth. What lies beneath Europa's crust may not just change science, it could change us. At first glance, Europa doesn't look like much. A small sphere, about the size of our own moon, orbiting the giant planet Jupiter. It's easy to miss among the gas giant's vast family of 95 known moons. But Europa is different, very different. And for decades now, scientists have been staring at it, captivated not just by its hauntingly smooth surface, but by what they believe is hidden below. An ocean. Not a lake, not a patch of melt, but a vast planetary ocean. One that may contain more than twice as much water as all the oceans on Earth combined. Water in abundance, trapped beneath an icy crust tens of kilometers thick. And where there is water, liquid water, there is always the tantalizing hope that something might be living in it. This revelation didn't come suddenly. It took years of painstaking exploration, some of it indirect, a puzzle pieced together from multiple missions, flybys, and analysis. The first hints came from the Voyager spacecraft as they passed by Jupiter in the late 1970s. Europa appeared smoother than expected, with strange dark lines etched across its surface like veins or scars. Scientists didn't understand what they were looking at yet. Then came NASA's Galileo spacecraft, launched in 1989 and arriving at Jupiter in 1995. Galileo was the first to orbit the gas giant and study its moons in depth. What it saw of Europa astonished the scientific community. The images were unlike anything we'd seen before. No jagged cliffs, no towering mountain ranges. Instead, Europa was eerily smooth. Too smooth. In fact, it holds the title of the smoothest object in the entire solar system. This smoothness tells a story. It means the surface is young, at least on a planetary scale. Most bodies in space are covered with craters, scars of ancient impacts. But Europa has few. The implication is that its surface is constantly being renewed, resurfaced by forces from within. This is where the mystery deepens. How could a moon with no atmosphere, so far from the sun, be geologically active? The answer seems to lie in a strange gravitational dance. Europa, along with the neighboring moons Io and Ganymede, is locked in a gravitational resonance with Jupiter. This creates tidal forces,
Barely
immense
reaching
ones.
500
Europa
meters
is
high.
pulled and squeezed with every orbit, its interior flexing like a rubber ball. This tidal flexing generates heat, enough to keep an internal ocean from freezing solid. As the Galileo spacecraft beamed back its images, planetary scientists began to notice something else. Long, straight grooves stretching across Europa's icy shell. These features, called lineae, are cracks, but they are unlike anything seen on Earth. Some extend for hundreds of kilometers, slicing through craters and ridges, suggesting they are relatively young. And they don't always match the predicted paths of stress caused by Jupiter's gravity. Instead, they twist, turn, and in some cases shift in ways that suggest the icy crust is moving over a liquid layer beneath. The ice may be sliding, grinding, colliding, creating patterns that look eerily like tectonic activity on Earth, except with frozen plates instead of rock. As we zoomed in closer, strange new features emerged. Some cracks didn't run straight at all, but curved, looping in graceful arcs. These cycloids, as they're called, are the product of Europa's constantly changing orientation as it orbits Jupiter. The tidal forces aren't just massive, they're dynamic, varying in direction and strength. The result is an ice shell that bends and fractures in curved patterns, with the double ridges on either side of the cracks, hinting at a process of repeated freezing and expansion. Over time, these ridges build up, creating some of the only elevation changes on Europa's otherwise flat face. And then there's the color. Europa, for all its pale beauty, is laced with reddish-brown streaks, especially around the cracks. These aren't random. Theories suggest that they are caused by salts and minerals, perhaps magnesium sulfate, or even sulfur compounds brought up from the ocean below and altered by Jupiter's intense radiation. The powerful magnetic field around the gas giant bombards Europa's surface with energetic particles, possibly creating chemical reactions that darken the material. If true, this would be direct evidence that the ocean is not just water, but salty, chemically rich, and possibly full of the ingredients necessary for life. One of the most compelling regions on Europa's surface is known as chaos terrain. Imagine looking at a patch of the moon where the ice has been shattered and jumbled, forming a mosaic of irregular shapes. Pieces of crust have broken apart, tilted, and refrozen in disarray. One of the most famous examples is Connemara Chaos. This area appears like a frozen accident, where blocks of ice have floated, drifted, and frozen in place. The most plausible explanation? Warm water from the ocean or a subsurface lake once pushed close to the surface, melted the ice above, and caused the overlying layer to collapse. It's like seeing the remnants of a frozen ocean quake, the aftershocks preserved in ice. But Europa's secrets don't end at surface features. Look even closer, and you find small, dome-like freckles scattered across the terrain. These are called lenticulae. Each one is about 10 kilometers across and rises subtly from the surface. They may be caused by warm ice or liquid pushing upward, rising through the cold shell like plumes in a lava lamp. Some scientists believe that beneath these features lie vast subsurface lakes, pockets of water entirely enclosed within the ice. These lakes could be isolated from the deeper global ocean and may even contain their own unique environments, chemical compositions, or just, maybe, primitive life forms that have never encountered anything else. As the evidence mounted, excitement grew. We were no longer just speculating. The images, the heat signatures, the gravitational models, they were all pointing toward the same conclusion. Europa is not a frozen wasteland. It's an active world, a world with liquid water, a world with heat and chemistry, and that means a world where life, in some form, might be possible. We still haven't seen beneath the ice directly. We haven't drilled or landed or dipped a robotic toe into the ocean. But every close-up image, every spectrographic analysis brings us closer. And we may not need to dig at all. Because in 2012, the Hubble Space Telescope spotted something remarkable. What Hubble saw changed the stakes. A fleeting wisp of something, barely visible against the cold black backdrop of space, arced above Europa's surface. Upon closer analysis, it wasn't an illusion or a glitch. It was a plume, a vast eruption of water vapor blasting out from beneath Europa's icy shell, rising more than 200 kilometers into space. For the first time, we weren't just staring at surface features or speculating about the chemistry below. We were witnessing a direct breach. The ocean within was reaching out. It was no longer locked beneath the ice. It was venting, perhaps regularly, right into the vacuum of space. This discovery electrified scientists. The idea that Europa had active plumes, like the geysers of Saturn's moon Enceladus, meant we wouldn't necessarily have to land and drill to sample the ocean. A spacecraft could simply fly through one of these plumes, capture particles, and analyze them. It's as close to direct access as we're likely to get without touching down. Suddenly, the timeline for unlocking Europa's secrets had accelerated. The possibility of detecting organic compounds, carbon-based molecules that form the building blocks of life, was no longer theoretical. It was on the radar, literally. Subsequent studies began tracking the timing and locations of these plumes, trying to determine whether they were sporadic or cyclic. And while the data is still incomplete, the evidence keeps building. Ultraviolet signatures captured by Hubble showed repeated
Barely reaching
bursts at similar
500 meters
longitudes.
high.
Magnetic field readings from the old Galileo mission, reanalyzed with new models, showed anomalies that could only be explained by localized eruptions of conductive fluid, likely salt water, breaking through the ice. Even the temperature data revealed warmer patches on the surface where a subsurface lake or vent might be located. The moon, it seemed, was alive. Not in a biological sense necessarily, but geologically, energetically, and chemically. And in the quiet vacuum above it, invisible forces were screaming. That scream did not go unheard. Two major missions were greenlit, both aimed squarely at unraveling Europa's mysteries. NASA's Europa Clipper and the European Space Agency's JUICE mission, short for Jupiter Icy Moons Explorer, would take different paths but with the same ultimate goal: to explore, observe, and understand Europa as never before. The Clipper, scheduled to launch in the latter half of this decade and arrive in Jupiter's orbit by the early 2030, is designed to perform dozens of close flybys of Europa, skimming just 25 kilometers above the surface. That's so low you could count individual ridges and fractures with the naked eye if you were bold enough to be on board. Equipped with a suite of high-tech instruments, Clipper will carry cameras with unmatched resolution, ice-penetrating radar to detect the thickness and structure of the crust, and spectrometers to analyze surface chemistry. It will also feature a magnetometer to help map the ocean's depth and salinity, and possibly most exciting of all, a mass spectrometer designed to sniff out any plumes it flies through. If a plume erupts during a flyby, and timing will be everything, the craft will literally taste Europa's ocean, atom by atom. It's not just about finding water, it's about finding signs of prebiotic chemistry, and maybe even biosignatures, molecules that could hint at microbial life. JUICE, launching earlier but taking a longer route, will focus more broadly on Jupiter's system as a whole, including Ganymede and Callisto. But it too will study Europa in detail, with its own set of instruments and close passes. Together, these missions represent the most serious attempt humanity has ever made to answer one of its oldest questions. Are we alone? And if the answer lies in Europa's depths, it would be nothing short of revolutionary. But there's more than just curiosity at play here. Europa's ocean isn't just liquid, it's likely salty, filled with minerals and chemical gradients. It may have hydrothermal vents on its seafloor, like the ones we find on Earth's ocean bottoms, black smokers that spew mineral-rich water heated by the planet's mantle. On Earth, these environments teem with life, thriving entirely independent of sunlight. Entire ecosystems with strange tube worms, bacteria, and crustaceans live off the energy provided by chemistry alone. Europa may be cold, but if tidal heating is sufficient, hydrothermal activity could exist. If that's true, then not only is life possible, it may be inevitable. On Earth, where we find water, energy, and the right chemistry, life always finds a way. The thought that the same could be true in an alien ocean beneath a shell of ice 500 million miles from the sun is staggering. Even the surface chemistry suggests complexity. Europa's crust may be interacting with the ocean below through cryovolcanism, eruptions of briny water that freeze instantly in the cold, creating new formations. The reddish material seen in the grooves might contain sulfur compounds, magnesium sulfate, or even organic molecules. Radiation from Jupiter complicates things, breaking molecules apart and potentially masking or altering organic signatures. But it also creates secondary reactions that might yield new insights. Understanding this surface chemistry isn't just a scientific exercise, it's detective work, one that involves separating native oceanic compounds from those produced by radiation or space weathering. And here's the kicker. Despite everything we've discovered so far, Europa remains a complete unknown in many ways. How thick is the ice shell? How deep is the ocean? Is it one continuous body, or is it segmented by rock or ridges beneath? Are there isolated lakes or pockets, shielded from radiation and pressure, where simple life might have evolved in silence for billions of years? Could there be microbial mats clinging to rocky outcrops, or even multicellular life? We don't know yet, but we're on the edge of finding out. What makes this moment so powerful, so historic, is that we are finally closing in. For decades, Europa has been just a hypothesis, a whisper of something more. But now we are approaching with eyes open and instruments ready. The images are already coming in, clearer and more detailed than ever before, captured by telescopes equipped with next-generation optics and sensors. We can see double ridges down to their texture, chaos terrain in 3 dimensions, subtle changes in surface coloration that hint at chemical diversity. And soon, we'll have data not just from above, but from within. Measurements of the magnetic field distorted by the moving ocean, temperature readings of warmer zones, perhaps even direct samples of material ejected into space. The story of Europa is no longer science fiction. It's happening. It's unfolding with every orbit, every observation, every burst of data beamed back from the edge of our solar system. And the deeper we look, the more we're forced to confront a possibility that was once too fantastic to believe. Life may not be unique to Earth. The universe, vast and ancient, may be filled with oceans. And in those oceans, life may be not rare, but common. As Europa Clipper and JUICE race toward their date with destiny, the excitement continues to build not just among scientists and
barely
engineers,
reaching
but among the
500
public
meters
as well.
high.
Something
This
about Europa captures the imagination in a way few celestial bodies do. Maybe it's the promise of an alien ocean world, or the eerie smooth beauty of its surface, or perhaps it's that feeling, the gut-level instinct, that this icy moon might be holding on to something truly transformative. Whatever the reason, interest in Europa is at a fever pitch, and as the imagery sharpens and the data begins to stream in, we are finally beginning to see it not just as a blurry moon orbiting a distant gas giant, but as a real place, a destination. And what we're seeing is extraordinary. The newest observations, gathered by powerful telescopes, refined imaging systems, and enhanced processing techniques, reveal a landscape like no other. Not just a smooth ball of ice, but a complex, fractured world. The double ridges, once only faint lines, now emerge in high resolution, showing layered edges and central troughs, possibly formed by repeated cycles of cracking and refreezing. These ridges stretch for hundreds of kilometers, forming networks that speak of tectonic stresses and moving ice. They tell us Europa is not dead. It shifts, it breathes, its surface is being reshaped from below. Even more haunting is the chaos terrain. Up close, these aren't just jumbled regions. They are puzzle pieces, rafts of ice that appear to have broken apart, rotated, and refrozen into new arrangements. They resemble icebergs adrift and later locked in place. The implication is profound. Something liquid or slushy beneath the surface once carried these slabs. The energy required to do this, combined with the speed at which these regions appear to reform, points again to that subsurface ocean being not just present, but active. Beneath the crust there is motion, there is heat, there is complexity. Lenticulae, Those small, freckle-like dots peppered across the surface have also come into sharper focus. Once thought to be just surface features, we now see evidence they may rise slightly, perhaps pushed upward by warmer material underneath. This diapiric movement suggests convection, a churning of the subsurface ice driven by internal heat. Imagine giant blobs of warmer ice or salty water rising through the colder matrix above, reshaping the surface ever so slightly. If these lenticulae sit above isolated lakes, they might offer access points, thinner regions of ice where future landers could reach liquid environments without drilling for kilometers. The chemistry is just as fascinating. High-resolution spectral analysis of Europa's surface has begun to identify more than just water ice. There are signs of hydrated salts, sulfur compounds, and possibly carbon-based molecules. These materials seem concentrated around fracture zones and chaos terrain, areas where exchange between the ocean and the surface is more likely. What this means is that the subsurface ocean is communicating with the outer shell, pushing materials upward. Some of those materials may have originated near hydrothermal vents, and if life exists near those vents, traces of it may have made their way to the surface, embedded in salt, frozen in time, waiting to be discovered. The radiation from Jupiter, intense and punishing, complicates things. It constantly bombards Europa's surface, breaking apart molecules and making it difficult to distinguish between original and altered chemistry. But even this challenge has a silver lining. The radiation also triggers reactions that generate oxygen and other compounds. If any of this material cycles back down through cracks in the ice, it could provide energy to support life in the ocean. On Earth, similar chemical cycling helps sustain entire microbial ecosystems. Europa, bathed in this interplay of radiation, chemistry, and internal heat, may follow a similar pattern. And then there's the magnetic field. Jupiter's immense magnetosphere induces electric currents in Europa's salty ocean, creating detectable magnetic signatures. By measuring these distortions, we can estimate the ocean's depth, salinity, and even motion. Recent modeling suggests that Europa's ocean might be 100 kilometers deep, 10 times deeper than Earth's, and under an ice shell 15 to 25 kilometers thick. That's a huge volume of water. And yet, it's trapped beneath this translucent, fractured crust. What lives there, if anything, is shielded from view, but perhaps not for long. The Europa Clipper mission is equipped with a magnetometer more sensitive than anything used before in Jupiter's system. It will measure these signals in high detail, using them to map the interior of Europa like sonar. If the ocean has layers, warmer zones, briny pockets, isolated lakes, we will know. And as Clipper flies through potential plumes, it will collect and analyze particles directly. Salts, organics, volatiles. Each molecule will tell a story. If we're lucky, some of those molecules might be unmistakably biological. But even if we don't find life, the implications are massive. The discovery of a world where all the ingredients for life exist, water, energy, and chemistry, would still be historic. It would mean Earth is not unique in its ability to support habitable conditions. And if Europa is habitable, what about Enceladus, or Titan, or other ocean worlds beyond our solar system? Europa becomes a Rosetta Stone, a key to understanding how common life might be in the cosmos. We've looked to the stars for so long, hoping to find someone, or something, looking back. But perhaps the answer has been orbiting Jupiter all along, encased in ice, quietly waiting. And now we're closer than we've ever been. The instruments are in place. The missions are on their way. The data is about to explode. Every pixel, every particle, every magnetic reading will peel back another layer of the mystery. And if that mystery leads to life, not as we know it, but life nonetheless,
barely
will forever
reaching
change our
500
place in the
meters
universe.
high.
The boundaries of biology will stretch. The definitions of habitability will evolve. and the idea of Earth as the cradle of all life will be at last redefined. Back here on Earth, we watch and wait. We tune in to mission updates, study the new images, and dream about what lies beneath Europa's icy skin. We name the fractures and craters, we speculate about the chemistry, we build models and simulations. But more than anything, we hope. Because Europa, cold and distant as it is, has become something more than a moon. It's become a mirror that reflects our deepest scientific questions, our boldest exploration goals, and our most profound longing to find that we are not alone. And as the images get clearer and the spacecraft draw near, that mirror starts to shimmer, not with fantasy, but with fact. Europa is real, its ocean is real, and the moment when we might finally touch, taste, or even hear the whisper of something alive beneath its surface, that moment is no longer a dream. It's a destination, one we're fast approaching.